and at the different locations. Glad to have you here. The intent of today's meeting is going to create an ability to share the science that's being done in the different modeling centers. With respect to the science, it is necessarily modeling in the Arctic that we are going to be focusing on. So we hope to hear from all the modeling centers that support large Earth system models. And we have 6 such centers doing their presentations today. And each center, from each center, a representative will talk about the priorities of Arctic modeling from their centers, what are their significant successes and challenges, and also they'll talk about what are ways they'd like to see more collaboration across modeling centers. So the 6 modeling centers that will be represented today are from NOAA's GFDL, DOE's E3SM, NSF's CESM, NASA's GMAO model, and NASA's GIST model, as well as from NOAA's EMC group. So I welcome everybody, and I look forward to a productive presentation and discussion at the end of this. The way it'll work is that every speaker will speak for about 9 minutes, and then we have about 1 minute for clarifying questions, after which we'll go to the next speaker. And at the end of it, we can have a more productive discussion about detailed questions. So with that, I'd like to start off with our first speaker. He's Mitch Bushuk from GFDL. And all the speakers, please introduce yourselves and look forward to these presentations. By the way, I forgot, I apologize. While Mitch is starting off, I'd like to also introduce my colleagues. The co-leads for the modeling sub-team are Richard Kalata and Wilbert Wire. So the 3 of us are the co-leads for this modeling sub-team. So welcome everyone, and over to you, Mitch.
Great, thanks a lot. So I hope everyone can hear me and see my slides. Get seeing a thumbs up. Great, so yeah, today I'll be speaking about Arctic modeling activities at the GFDL. My name is Mitch Bushuk, so I'm working on sea ice modeling, prediction, predictability. And the stuff I'm going to talk about today is really the culmination of a huge effort from many, many scientists at GFDL. So I'm just kind of the talking head, but I do not claim credit for most of these achievements. Okay, so we were given 4 prompts for this presentation, and I'm going to attempt to quickly say some things about each of the 4 main prompts. So that the first one was on what are our priorities for Arctic system modeling. So at GFDL, we have sort of 3 mutually interacting high-level priorities. The first is development of coupled Earth system models. The second is using those Earth system models to understand climate variability and change. And the third is making predictions and understanding predictability of the Earth system. So on this first point, GFDL has a number of in-house component models, namely the MOM6 ocean model, the SIS2 sea ice model, the AM4 atmosphere model, and the LM4 land model. And then we're running these models in coupled configurations to produce experiments for big activities like Cm4, for example. And these experiments are used to understand Arctic variability and change across a number of different metrics and areas, such as sea ice, ocean dynamics, atmospheric dynamics, icebergs, Arctic amplification, primary productivity, and wildfire extremes, just to name a few. And then on the prediction side, we're running initialized near real-time seasonal predictions at GFDL. And we're also running initialized decadal predictions. And the main foci of the prediction effort is on Arctic sea ice, Arctic ocean properties, biogeochemical variables, and land snow cover. Okay, so I'm going to make a few comments on some of the kind of successes and achievements over the past years at GFDL. So one major success has been the, oops, getting a little chirp there. One major success has been the development of a unified suite of climate and Earth system models. And it's unified in the sense that all four of these models shown here are global models that share the same model components, but are set up, they're geared towards different timescales and different functionalities. So this shield model just uses a simple mixed layer ocean, and it's really geared towards weather and subseasonal forecasting. Then we have this model called SPEAR, which is built for seasonal to decadal prediction and predictability activities. SPEAR uses a full 1 degree, 3-dimensional ocean. We have an ocean data assimilation system that we run with SPEAR, which we use for initializing seasonal forecasts. And then our two main sort of climate timescale models are Cm4 and Esm4. Cm4 is more of a physical model, and it employs a 1/4 degree ice ocean resolution. Esm4 sacrifices some ocean resolution, so it uses a 1/2 degree ocean resolution, but it uses the extra computational resources to run a more complicated so-called cobalt biogeochemical model, and also employs fully interactive atmospheric chemistry. So I'm going to highlight a few quick successes that we've produced with these suite of models. So in terms of Arctic sea ice, the models do fairly well in terms of the sea ice extent, mean state, and trends. So on the left here, I'm showing the Cm4 sea ice extent climatology in the Arctic, which matches the observations fairly well. And then on the right, I'm showing large ensemble simulations performed with the SPEAR model, where the green time series here show the observations in March and September. And you can see that the large ensembles capture the observed decline quite well in both winter and summer. And the observations tend to live within the spread of the ensemble variability. So the ensembles seem to be consistent, at least with the observed record. There's also been some interesting recent work using Esm4 to project Alaskan wildfire risk. So Esm4 contains an interactive fire model, and you can use that model to produce a time series of historical burned area in Alaska. And this was used in a recent study to state that Alaskan fire risk has increased by roughly a factor of 3 in recent decades relative to this earlier 20th century period. The ESM framework is also being used to understand physical biological feedbacks in the Arctic system. And there was this one interesting recent study where interactive nitrogen was added to a climate projection simulation. And it was found that by adding interactive nitrogen, it led to enhanced Arctic warming and enhanced sea ice losses relative to a run that did not include this interactive nitrogen component. And this was due to a physical biological feedback between enhanced chlorophyll in the surface ocean, and then a corresponding shortwave heating and a shortwave albedo feedback that resulted due to that interactive nitrogen. So that's kind of an interesting example of biology not just being controlled by the physics, but the biology actually impacting the physics as well. We're also doing a lot of work on seasonal predictions of Arctic sea ice. Shown here are predictions of September sea ice extent, with the observations shown in black, and then the different colors showing predictions at different lead times. And you can see in both the SPEAR medium system as well as this earlier floor system, we have skill at capturing both the downward trend in sea ice, but more importantly, we can predict with some skill these interannual fluctuations in sea ice extent. And these values in parentheses here indicate the detrended anomaly correlations. So you can see that there is indeed some skill in these predictions. We've also been doing a lot of work using data assimilation and prediction to help evaluate the Arctic observing networks. So in the study on the left here was looking at the impact of surface and subsurface ocean observations on sea ice prediction skill. And what we found was that by including ocean data in our data assimilation, we got notable improvements in prediction skill. This was associated with both SSTs as well as subsurface data. And the biggest improvement came from subsurface observations from CTD measurements. And then this panel on the right here is showing the impact of assimilating sea ice concentration observations. And we find that by including sea ice concentration observations, we get an improvement in forecast skill, as you might expect. And that improvement is mostly on the sub-seasonal timescale. So we get an improvement from lead times of 0 to 6 weeks in advance. And then we get this convergence at around the 6-week lead time. And it's at that lead time that other sources of predictability really take over. Okay, so now a few comments on challenges. So the GFDL models have had a number of very persistent Arctic biases across model generations. And one I want to highlight here is this bias in sea surface salinity. So if you look at our sea surface salinity biases in the global ocean, the Arctic Ocean really stands out as having this very offensive positive sea surface salinity bias. This is also seen in ice ocean models. And you can see that all these various ice ocean models from this study all display this same too salty surface bias that we see in the GFDL models as well. We think this is probably being caused by too much vertical mixing, which is mixing warmer, saltier water across the Arctic halocline. But we're working on that, and we would like to interact with some of you on trying to improve these biases. Two other biases I want to highlight is the sea ice concentration bias that exists in the Barents and Jin seas, where our sea ice is simply too extensive in these seas. And we think that could be caused by either too little northward heat transport by the ocean, especially given that we're running fairly coarse resolution models, which don't resolve the eddy heat transports. Or potentially it could be due to too much sea ice export through the Fram Strait, or some combination of these two factors. We also have this fairly egregious bias in terms of our sea ice thickness spatial pattern. And you can see that the Cm4 model, instead of having the thickest ice north of Greenland and the Canadian archipelago, we're advecting our thick ice into the Beaufort Sea and the Chukchi Sea. And we think this may be due to rheological errors in the ice model. It's notable that even if you run the same ice ocean model with reanalysis winds, you get a very similar spatial pattern of sea ice thickness. So we have a hypothesis that this might be due to the ice not having enough shear strength and it being too easy to advect the ice into the Beaufort Sea, but we still need to look into this more closely. There's also a number of challenges associated with land and biosphere modeling. One of those being the representation of terrestrial ecosystem shifts and land climate feedbacks. So that these plots on the right here are showing ESM4 projections of changes in tree cover. And what you see is that in this scenario simulation, there's a notable greening of the Arctic boreal forest. And you can imagine that with this greening, there's going to be a large impact on surface albedo, and then an associated impact on the entire global climate system as a result. Some other challenges include the representation of peatland and permafrost carbon fluxes coming from CO2 and methane in both the Arctic boreal zone as well as the tundra. Another challenge is the representation of aerosol snow albedo interactions and climate feedbacks. And then on the biogeochemistry side, we're very interested in improving our regional modeling capabilities for biogeochemical ecosystem modeling for Arctic and Bering Sea forecasting applications. Okay, and now this is my final slide. So regarding current and potential collaborations, I think there's a number of interesting avenues we could go here. First of all, GFDL, NCAR, and EMC are all developing and using the MOM6 ocean model. And I think there's a nice potential there to potentially collaborate on these Arctic Ocean model biases and try to make sure that the ocean model is being formulated in a way that makes sense for the Arctic. GFDL and EMC have a recently planned joint project on sea ice data assimilation techniques, looking at the impact of sea ice model physics on forecast skill, and also comparing seasonal sea ice predictions. So we had planned to do this between our two centers, but if other centers are doing sea ice prediction research, it would also be great to have others involved in this as well. Another potential area of collaboration is the use of the IcePack sea ice column physics package. So GFDL SIS2 lacks a lot of model complexity relative to SICE version 6. So SIS2's model physics are more similar to SICE version 4. And so we're very interested in incorporating some of the more advanced physics available in the IcePack package. We started doing some of this already, but we would love to interact more closely with the IcePack team and keep pushing our physics forward. And then a final possible area of collaboration is a collaboration on the numerical challenges associated with coupled ice ocean numerical instabilities. Bob Hallberg's been furiously working on this for about a decade or so, and he has a lot of good thoughts on it. And he's mentioned he's very keen to interact with others on this topic. So that was kind of a rapid fire introduction, but if anything piques your interest, please get in touch with us, and it would be great to carry this conversation forward. I've listed 3 names and emails here for points of contact. And I think with that, I'll wrap up and pass it off to the next speaker.
Thanks, Mitch. Any clarifying questions from the group as we switch over to the next speaker? The next speaker is Luke Van Rokel from E3SM. I don't see any raised hands. And we can have more of a discussion of the activities that we can work on together at the end. I think we can switch over to the next speaker, Luke Van Rokel from DOE. And are you able to share your slide, Luke?
I'm working on it right now. I have a system preference issue. It looks like I'm going to have to drop out of the meeting and come back in. Could I go down one in the agenda?
Yes, what we'll do is we'll move you to the end and then go down the list, and then you can come in after that.
Sounds good. Sorry about that.
No hassles. So now we move over to the next modeling center is CESM, and Marika Holland will do the presentation. So over to you, Marika.
Thanks, Renu. Okay, so hopefully everyone can see my slides okay and are seeing the version without the notes.
That looks good.
Great,
Thanks, Marika.
Thank you. Yeah, so I'm Marika Holland. I'm a scientist at NCAR, and I'm also the co-chair for the CESM Polar Climate Working Group. So I'm going to be speaking with you a bit about some of the CESM priorities for Arctic system modeling. And just similarly to what Mitch said, this is very much a group effort. And so this talk I'm going to be giving has a lot of input from other working groups under the CESM umbrella. Okay, so just to familiarize you, CESM is very much a community model. We have community governance through a CESM advisory board and steering committee. And we also have 12 working groups. And those working groups oversee the development of the model and also application of the model to a variety of science questions. So these groups work very closely together to develop CESM and also use CESM. And again, it's used for a very wide range of science questions. You can see the different working groups here in these sort of lollipops, and you can see that it kind of encompasses everything from, paleoclimate to biogeochemistry to land ice, et cetera. Many of these working groups have a specific interest in Arctic system modeling. And there's also a lot of cross-project activities that have some emphasis on Arctic system modeling. So I'm going to try and highlight some of those. So in terms of an overarching priority for Arctic system modeling, CESM's overarching priority is to improve Arctic system processes, develop new model capabilities, and support community science in the application of CESM to understand and predict the Arctic system. So this includes model developments across all of the components, exploration of and support for new Arctic system model configurations, performing and providing simulations. Many of these have wide application, but have some relevance for Arctic system science, and also providing the tool, the model itself, and resources in terms of tutorials, liaison support, diagnostic capabilities for community-driven science with CESM. So I'm going to go through some kind of topic areas, and then I'll talk about some cross-cutting projects in the context of Arctic system modeling. So from the atmospheric side, there's been some recent achievements in terms of improving the representation of clouds within high latitude regions. and in particular, producing simulations that have more liquid containing clouds. So a better simulation of mixed phase clouds. And of course, this has impacts on the surface radiation budgets. We also are putting together variable resolution refined Arctic mesh simulations. And you can see an example of that here on the right-hand side, where there's very high resolution over the Greenland ice sheet, high resolution over the Arctic basin, and all of this is embedded in a 1 degree global grid. And the focus of that work is really to improve the Greenland ice sheet mass balance, and also to look at Arctic extremes and the simulation of those extremes. And you can see on the bottom panels here an example of improvements in Arctic extremes in terms of precipitations within storms. So this shows PDF of precipitation for June, July, and August. The Arctic grid is in red here. The black is ERA 5, and then the blue is sort of our coarse 1 degree resolution grids. So you can see that there's considerable improvement in Arctic extremes using these refined grids. Some of the challenges that we face, and some of these are long-standing issues, are the atmosphere ice sheet coupling and that two-way coupling. Surface radiation budgets and how well those are simulated, precipitation phase, and cloud feedback. So you can see still a lot of emphasis on improving clouds within our simulations. In terms of existing collaborations, we have very strong collaborations with the university community. There's also strong collaborations across NCAR. So CESM is largely housed within the Climate and Global Dynamics Lab, but there's a unified modeling project at NCAR to unify our modeling infrastructure across our weather scale and climate scale activities. In terms of Arctic land ice, some of the recent achievements are that we now are running CESM2 simulations with an interactively coupled Greenland ice sheet. This is using the community ice sheet model. And this is being used to look at future ice loss. And you can see an example of that on the right-hand side here, the surface mass budget of the Greenland ice sheet. We're also doing long transient simulations of the Greenland ice sheet evolution during the last interglacial. Some of the modeling challenges that we're tackling are how to better represent ice calving and ice-ocean interactions, and also extending our land ice simulations to Northern Hemisphere paleo ice sheets to look at the last inception and deglaciation. Some of the collaborations that we have in this area are with NORSE, the Norwegian Research Center, looking at future Greenland ice sheet evolution, and also in terms of paleoclimate studies with Alex Robinson at the University of Madrid. In terms of Arctic sea ice, so our priority areas are trying to understand predictability of sea ice across timescales, so from seasonal out to century timescales. There's a lot of ongoing work looking at the role of sea ice in the global system, so coupled climate system, but also interactions with biology, and more and more effort on stakeholder interactions and impacts related research. We also have efforts underway to improve the process representation within our sea ice model. And there's a particular focus on the subgrid scale heterogeneity of sea ice, things like snow fractional coverage, melt pond characteristics, et cetera. Some of the achievements in the area of Arctic sea ice are in the quantification of prediction uncertainty and predictability characteristics of sea ice, again, across timescales. There's also a lot of nice community-driven science on factors driving historical ice loss. For example, the role of wind forcing versus other forcings in driving sea ice loss in the Arctic, and the role of various forcings, things like biomass burning, greenhouse gas emissions, et cetera. Some of the challenges that we face are supporting multiple community projects in the use of CESM to understand Arctic sea ice variability and change, and also building new collaborations. So we really do have a lot of interest in impacts related research, which requires collaborations with new types of scientists, people, economists, infrastructure experts, et cetera. And so there's challenges in building those collaborations. In terms of the collaborations that we have very strong collaborations with the SICE consortium. We're actually a part of the SICE consortium. And so the SICE consortium includes individuals from, or includes a number of different modeling centers. We also have strong collaborations with observers that were at Mosaic and also with the university community. In terms of the Arctic land system, the overarching or primary priority in the land system work is to better represent the permafrost carbon feedback. Of course, that's quite complex, and it includes a need to better simulate the soil climate, including hydrology, snow cover and its insulating impacts, biogeochemistry, and vegetation. In terms of achievements, some of the recent achievements have been the representation of vertically resolved soil biogeochemistry, hill slope models that simulate improved subgrid scale heterogeneity in permafrost and hydrology, and also work on improving the ecosystem response to disturbance, to fire primarily. So in terms of challenges, there's still a lot of ongoing challenges in this work in representing, for example, soil biogeochemistry. So that a lot of this is ongoing work. There's also challenges in terms of impacts research and links to stakeholders similar to the sea ice related work. In terms of collaborations, there's strong collaborations with Norwegian scientists under the NOR-ESM effort, the university community, and also the Permafrost Carbon Network. Okay, so we also have a lot of cross-working group projects that are of relevance for the Arctic. So there's a strong effort on understanding fire in a changing climate, the role of different forcings, volcanic, greenhouse gases, aerosols, et cetera, on high latitude climate, interactions of Arctic cyclones, atmospheric rivers, and sea ice. And then we have a lot of work in the area of prediction using our large ensembles and our initialized prediction ensembles, which we produce and make available to the research community. And so those ensembles are being used to understand initialized prediction and predictability characteristics and changes in extreme events within the Arctic. We also have a lot of effort in data assimilation capabilities and building a coupled data assimilation system. And I did want to note, I added this at the end here, that I've only touched on some subset of the activities underway. There's a lot of other work in the area of Arctic system science that is being done under the CESM umbrella. So this is my last slide, and I'd be remiss not to mention the fact that one of the main priorities of CESM is to enable community science. And we do this through many different efforts. We have tutorials, we have liaison support, we make available many, many simulations and diagnostic tools to assess those simulations. We provide a robust and supported research tool in the model itself. And our working groups are open to all interested participants. We have regular meetings. So I'd encourage people to get involved as well. So I know we're not really taking a lot of questions, but I'll just leave this up there and thank you for your attention.
Thanks, Marika. If you have any clarifying questions, please speak up. And we'll have time for detailed questions at the end.
Maybe I will have a quick one. This is Hai Long. Thank you for the interesting talk about the CESM. So I'm wondering, in your Arctic refined mode, you said that is a good improvement in the extremes. Are those mainly due to the finer resolution for physics, or is there any problem with the transport from lower latitudes?
I think so. Those are very much in the research realm right now. And so a lot of, especially work on coupled simulations with that refined grid are ongoing currently. I think it is a better resolution of weather systems entering the Arctic. I mean, if you just look at these very cool animations from those simulations, you can see storms entering the Arctic. So it might also be related to the higher resolution, physics within the Arctic itself. So it's probably a combination, but I'd say that there's still more work ongoing in that area. And Adam Harrington is the one that's leading a lot of that work at NCAR. So I'd encourage you to also contact Adam with more questions.
Great, thank you very much.
Yep.
There's one more question from Jack Pidd.
This is kind of a question for both speakers, and I would thought it might be for all four of them, but I was just curious.
So-
I'm not an expert. Go ahead.
So Jack, if that's the case, can we wait till the end of all this and then we can have you go first?
Sure.
Is that a good approach? Because this is just time for clarifying questions. In the meantime, I'd invite Richard to, Richard is going to be doing the presentation. Richard Kilometer will be doing the presentation from NASA GMAO. So Richard.
Hello, can you hear me?
Yes.
Okay.
We can't see you though.
Let's see. Okay. Can you see my slides?
Yes, thanks.
Okay. And so Lauren Andrews had a small family emergency, so I'm going to try to pinch hit for her. My name is Richard Kilometer. I'm an MST co-lead. I'm with the University of Maryland and the GMAO, and I'll try to do my best here. So the Global Modeling and Assimilation Office is, oops. Oh, I can't, oh, there we go. Okay, the Global Modeling and Assimilation Office was formed from a merger of the Data Assimilation Office, which was a routine numerical weather prediction based effort supporting the NASA EOS mission, and the NASA NSIP, the Seasonal to Interannual Prediction Project. That was back in 2006, if you remember NSIP. So the GMAO provides a variety of data assimilation and numerical weather prediction products in support of a wide variety of NASA efforts. Many of these products begin with the Goddard Earth Observing System model. The model components allow it to run as an AGCM coupled with either the GFDL ocean model or the MIT GCM as an AOGCM. Also as a chemistry climate model, the CCM, or the chemistry transport model configuration, the CTM. So among the products that the GMAO produces are a near real-time forward processing or FP analysis as a routine numerical weather prediction system, a subseasonal to seasonal system that is currently coupled with a version of the GFDL ocean model. We also have a coupled version with the MIT GCM, as I said. We have a high resolution composition model that produces an NWP forecast daily. That's called the CF model that depicts 240 gaseous species. It's run at very high resolution. I believe it's 25-kilometer resolution. That's in addition to the constituents and interactive go-kart aerosol transport that's used in our numerical weather prediction model. We also run retrospective and current analysis systems in support of various satellite products. So for example, we provide atmospheric profiles for the Ceres team, for I think it's now 24 satellite teams at NASA. And we also produce, of course, climate reanalyses such as MERA-2. Okay, so the GMAO subscribes to the integrated Earth system analysis approach. So there are several model components that and development that is related to this. We have significant relation with the NASA Biosphere Sciences Laboratory for biogeochemistry and carbon cycle modeling that have relevance to subarctic land surface and Arctic Ocean modeling. The GMAO is a member of the Joint Center for Satellite Data Assimilation, the JCSDA, and the development of the next generation JEDI data assimilation system. So as part of JEDI, We are developing the sea ice ocean coupled assimilation system known as SOCA. We are also participating in a NASA project called Polar Mera, which is joint with the NASA Cryospheric Science Lab to improve the representation of Arctic and polar processes in future numerical reanalyses. So these slides, I believe, are examples of each of those things. The first one is associated with our FP numerical weather prediction and analysis near real-time system. So twice daily, we produce a numerical weather prediction forecast at 12-kilometer resolution currently. And we produce associated analyses, which can be used in near real time for the assessment of particular events. So in the animation on the left here, we show an animation of the European heat wave, which occurred, or the Eurasian Siberian heat wave, I'm sorry, that occurred last year over Siberia. And so you can see the various warm temperature anomalies that are associated with that over Siberia. The contours also show the aerosols that are associated with forest fires in those areas. And so those are assimilated based on NASA satellite data. And so you can see the interactive aerosols going on in these simulations as well. The figure on the right shows an event in 2019 in which there was widespread surface melt over the Greenland ice sheet, including at Summit, Greenland, which has only happened very rarely. This event began as a heat wave over Western Europe, and then transited to the west and went over the Greenland ice sheet. So these pink areas here over the Greenland ice sheet are showing the surface melt area over the ice sheet, and then eventually it starts to fill in towards the highest elevations of the ice sheet. So as far as one of our impactful achievements, I think our representation of the surface processes over the Greenland ice sheet have been very successful in representing surface mass balance and also surface temperatures over Greenland. The MERA-2 reanalysis remains the most accurate, regularly gridded reconstruction of surface temperature that is available. And it provides a realistic representation of Greenland's surface mass balance. Okay, the next slide here shows our subseasonal seasonal prediction system in the Arctic. So we're currently in the process of upgrading our systems from version 2 to version 3. Version 3 will implement the MOM5 model at a much higher resolution. It will also include an advanced ensemble member scheme for looking at subseasonal and seasonal forecasts. So the ensemble system will begin with 40 perturbed ensemble members. And based on the analysis of those ensemble members, they will be subset to run over the seasonal forecasting period. So this animation, slow animation, is kind of a demonstration of how that ensemble member works. M2 Ocean is the ocean analysis, and from that you get a set of ensemble members for various days throughout the particular month for the seasonal forecast. And from those, they are then subset at the end of this to produce the seasonal forecasting system. So our tests have shown that this is a superior system. We also have done several improvements to our seasonal forecasting system. And so we're very much looking forward to this new seasonal forecasting system, which will be implemented either later this year or into next year. Oops. This is a comparison of our seasonal prediction for Arctic sea ice. So we have a lot of difficulty in our routine forecasting system for Arctic sea ice. It seems to have a lot of inertia as far as predictions. So if you look at these open dots, for example, in this plot, they are the initial conditions for the sea ice, which tends to drift off to the side rather than following the analysis points. We get a much better agreement with the new version 3, and that's due to improvements in the surface albedo, and also a higher resolution ocean, we think is also improving those representations. So currently for the sea ice outlook, we submit a offline forecast that's not part of our routine forecasting system. In that offline forecast, we ingest Cryosat-2 for our initial ice thickness observations. So we're hoping to do away with that with our new system. We've done some comparisons, and we believe that our new analysis system will be competitive then with what we can do with offline assimilations and various tweakings. On the right here, we show our representation of the skin temperature from various forecasting tests. And I think in comparison to version 2, which is shown in the third column here, version 3 shows a colder values over the top of the ice sheet. It seems to agree much better with MERA-2 and with MODIS satellite data. So we believe we're getting a much better representation of the Greenland ice sheet in the new seasonal forecasting system. So as I mentioned, we have significant collaboration with the Biospheric Sciences Laboratory, and those investigators are working on wetland methane emission model development. Part of this is associated with our support for the NASA Above mission, which was a field study conducted in the Arctic over the last several years to look at biogeospheric chemistry over the Arctic. And so a lot of effort has been put into that. Okay, and as I said, one of our new one of the major things that we're working on is our support with the development of the JEDI data assimilation system. We're members of the Joint Satellite Data Assimilation System, Joint Satellite Data Assimilation Center. Oh, sorry, we're 9 minutes?
Yes, past 9 minutes, yeah, so thanks.
Okay, I'll try to finish up quickly here. So this is showing that with our new joint atmosphere ocean data assimilation system that's in development here, we're getting a much better representation of the ice edge in the North Atlantic than you would with the free running model. As I mentioned, we're part of a project called Polar MERA, which is joint with the Cryospheric Science Lab at NASA Goddard. And so there are 3 stages of that. It's to comprehensive assessments to improve polar processes in the GEOS model. For our next reanalyses, which is the 21st century reanalysis R21C, that'll begin production in 2021-22. We're going to produce a product which is based on R21C at high resolution that will experimentally involve additional polar processes for the improvement of the representation of the cryosphere. And future directions. So the GMAO is working towards a fully coupled Earth system model for both reanalyses and forecasts. So the limitations, we believe it for the Arctic are observational limitations that affects our data assimilation. It also affects how our improvements to our models, because we have less data to improve parameterizations and associated things like that. So things that we're working on are an effective integration of Arctic freshwater hydrology into our coupled models that would include coupling with we have a capability for coupling with the JPL ISSM ice sheet model. We'd like to improve our Arctic freshwater representation using that and other developments for improving the freshwater representation of the Arctic. And other areas that we're working on are improved predictability and predictive skills and the assessment of Arctic mid-latitude connections. And I think I should stop there. Renew, you're muted. Sorry.
Mute. I think as Renew unmutes Maxwell, you can go ahead and queue up your presentation.
Thank you. I had the roughest time unmuting. So Max, looking forward to your presentation, and Max is from NASA GIS. So take it away.
And Max, you're on mute if you.
Hello, everyone. Today I'll be talking about Arctic modeling at NASA GIS, and specifically what that means in an institute that is as small as GIS. So yeah, I'm presenting material on behalf of many GIS and Columbia University folks, as well as from other universities and centers. So yeah, a few introductory remarks. Apologies for not having a schematic of all of our model versions and all that. I spend most of my hours writing code for our climate model, and someone had the notion that I should start giving overview talks. So this is my first time giving an overview talk in quite some time, so I hope you will excuse a little bit of stumbling and bumbling. So back to GIS. It's as a relatively small institute with rather few Arctic specialists in its ranks. We do have a few polar-oriented folks at the moment. Our quote-unquote Arctic findings tend to occur as part of larger analyses of large-scale modes of variability and patterns of response to climate change. Sorry, I was just checking the chat. Yeah, so on that theme of larger scale patterns of larger scale modes of variability, GIS has a long history of analyzing the response to anthropogenic radiative forcing, and in particular the response of changes to latitudinal temperature gradients for Arctic annular modes and Antarctic and so on. So since those early days, many self-generated modes of simulated variability have come into the model. And so, and the QBO, for example, and the untangling of all these interactions has been quite fascinating for GIS dynamicists. So this panel, this plot is showing a compositing of the response of 500 millibar geopotential height to El Nino and La Nina, broken down by QBO westerly and easterly phases. And finally, the first and third columns are for prescribed composition, and the second and fourth for interactive composition. So it does, so yeah, focusing on the lower left two panels, you can see that the second column has a stronger response over the Arctic being at the center of these plots. Sorry for the small size. For El Nino responses, the response of the Arctic to El Nino during easterly QBOs, and likewise, somewhat of a mirror image, the upper two right panels for La Nina and the westerly phase of the QBO. Other kinds of variability involving the Arctic. So we relatively recently, James Williams has joined GIS, who is our resident sea ice dynamics expert. And yeah, part of the exploration of teleconnections is the construction of good metrics for them. And so we believe that if we can coax our model to replicate this particular correlation pattern, we will learn a lot. And this correlation pattern is showing from observations and reanalyses, the correlation of ice cover with Fram Strait export. So the red colors unsurprisingly indicating more ice when there's more export through Fram Strait. And where are the negative anomalies? They're in the Siberian sector. And James says that this is not very well simulated in models, and it will be a challenge to do so. In the interest of time, I think I'll really gloss over the right two panels quickly because they are rather more oceanic. But in passing, I'll say that we have done a lot of investigation of AMOC, Atlantic overturning collapse behaviors in future climate runs. And there's quite a lot of variability among model versions, and even within ensembles, there's a lot. And what we have not yet explored quite as much is the impact of all of that on the Arctic and the participation of the Arctic in this variability. We're finding some interesting correlations between recovery and the transport through various straits in the archipelago and Nari Straits, which we hope to find some evidence for much smaller in magnitude in the historical period. In this plot, we see two ends of the spectrum of the kinds of analyses being done for sea ice. So on the left, we have the typical historical trends. In the interest of time, I won't say much about those other than that we are doing respectively well. On the right, we have the intricacies of ice dynamics that James is delving into using ice bridge data. And only James can explain how he is using this data to back out unconstrained ice dynamics parameters. I'll just explain that the plot shows ice thickness as a function of latitude with Greenland on the left, and he's somehow using the gradient within that red ellipse to figure something out. So James is in the meeting today, and you can ask him questions about that if you're curious. And in the middle of the spectrum, there's no plot on this slide about it, is the basically that we spend most of our time trying to improve the Arctic climatology, the seasonal cycle, and so on. I think Mitch alluded to the fact that coarse resolution models have the problem of there being too much ice. And this is something we have spent uncounted hours grappling with. And we don't expect that any one change to the sea ice model will work miracles, given that the atmosphere and the ocean have so much control over temperatures in the Arctic. But now and then there are some interesting changes to sea ice processes other than bug fixes, which have a big impact. So recently, Zhanghai Jin, who I believe is also in the meeting today, has joined GISS. Zhanghai is a radiative transfer specialist, and he has tackled a number of issues in our radiative treatment of sea ice. So his ambitions are to develop a comprehensive treatment of light scattering through sea ice. And so in his first attempt at that, sorry for the small panel size, small plot size there, but it definitely increased seasonal melting, and the increase of the seasonal cycle is not desirable compared to observations, but it's moving the annual mean in the right direction. So he can tell you more about his work on this topic. I'll just say that since we don't have a unified radiative transfer scheme throughout the ice atmospheric column, Zhanghai is also factoring in cloud scattering effects for the treatment of sea ice albedo. Moving on to atmospheric composition. Another radiative aspect of the Arctic, the aerosol forcings there. GISS has some history in modeling black carbon effects on Arctic snow. The Arctic aerosols in our latest model runs haven't yet been analyzed much by GISS aerosol specialists, but some other groups have led some detailed work there. This plot shows the time evolution of the burdens of black carbon, organic carbon, and sulfate, both for CMIP emission scenarios and alternative ones. Please contact Kostas Tsigaridis. The spelling of that is at the bottom of this slide if you are particularly interested by this type of modeling. While our very busy aerosol modelers do not focus much on the Arctic themselves at the moment, they do conduct very detailed analyses of our historical runs using available data, some of which is in the Arctic. And these plots show comparisons of modeled sulfate deposition at ice core locations to measured at Greenland and Svalbard. So as you saw in the previous slides, Arctic aerosol loads are generally—
So, Max,
yes?
can we rush through it a little bit? Thanks.
Yes. As you saw in the previous slides, Arctic aerosols are generally decreasing, but this is not going to be the case for fire-related aerosols. We have begun to expand our capabilities in fire modeling. Part of that is depicted on the right, which is a schematic of our fire model, which is still being tested and calibrated. On the left is an attempt to assess our model skill given some prescribed emissions from wildfires for the month of July 2020. There are some issues in estimating fire emissions from observations, which Robert Field would be happy to tell you more about, and those issues could be leading to somewhat of an underestimate of aerosol optical depth in this sensitivity study compared to MODIS. Moving on to clouds. Clouds have been a major focus of parameterization development in our latest Model E3 version, which we're calling Model E3. As you all know, cloud phase feedbacks are a hot topic at the moment. I won't try to cover that space today, and others I guess are far better at it. What I will try to convey here is a sense of the techniques we are using to attack this question and a couple of Arctic examples. Cloud phase is one of the metrics we feel is most improvable in E3 relative to previous model generations for structural reasons. We have adopted a microphysical scheme, MG2, which represents mixed phase processes far more comprehensively than does the E2.1 scheme. And we have a suite of case studies and remote sensing metrics that we think provide a coherent basis for optimizing our parameterizations. Despite this encouraging progress, there remain a number of barriers to further progress. First and foremost being that the fundamental physics of ice formation processes remain fairly poorly understood. And in the mixed phase routine, this means that the primary sink of supercooled water is poorly understood. Another hurdle is that Arctic clouds can often be extremely thin, i.e. subgrid
Sorry,
scale.
Max, to jump in, we're out of time. So if you have one or two sentences, or you could continue the discussion in the chat or drop your email in there.
Okay.
Sorry about that, Max. But you can continue speaking a little bit as we transition over to Hendrik, you can continue speaking until Hendrik's slides are shared. So. Okay, sorry, hopefully we'll have time to come back to this and hear more about what GIS is doing. Otherwise, people have the option to go to the slides directly. Looks like Hendrik has shared his slides, so take it away.
I even unmuted myself eventually. Can you hear me?
Yes, thanks.
Can you see my slide?
Oh, it's not in projection mode yet.
No, it is. We can see it.
Okay, thank you. So my name is Hendrik Tolman. I'm a longtime employee from the National Weather Service. I spent most of my career in the Environmental Modeling Center as a marine modeler. Eventually have been serving as the EMC director for a few years. I'm now at headquarters, basically the senior advisor for our modeling strategies. And to tell you how small this world is, I grew up in the Netherlands. I came to the US for a postdoc at NASA Goddard. And I used to play volleyball in the early 90s with Andrea Mollett every lunch break. And then my neighbors at NASA Goddard were Brian Gross as a postdoc, who later became the deputy director of GFDL and now is the director of the Environmental Modeling Center. And my other, his roommate was Wayne Higgins, who is now the director of the Climate Program Office at NOAA OAR. I am just like many others, or I've already said, I'm just a speaking head here. There are dozens, if not more than 100 people working on the systems that we're working on, both inside and outside of NOAA. And so I'm not taking credit for that work here. I'm just a speaking head and a point of contact. I'm the point of contact at headquarters, and in the agenda, the other point of contact for EMC is Vijay Talapragada. Bottom line up front, we actually have had relatively recently developed Arctic requirements. We didn't used to have them. They basically say that from a service perspective, for the weather service particularly, we need to have consistent ocean atmosphere and ice products, which implies that we really need to do coupled modeling. For us, it's a different scale of time of forecast that we're looking at than most of the other groups that have been talking here. So we're really talking to predictions up to about a year, and we are mostly on the physical environment. So the carbon cycle is something that we don't look at, although we are looking at some ecosystem issues like harmful algal bloom and stuff like that, as it has impact on our forecast. Because of the fact that we have a focus really on the best possible forecast, with a focus on the weather forecast, I've structured my talk a little bit different than the other ones, and I talk a little bit more about our strategies and ways of going forward and our accomplishment with that, and a little less on science bits and pieces. The second upfront bottom line issue is that we used to be a shop that did a lot of our work ourselves. We are really seriously moving to community modeling on all fronts, and that is the unified forecast system approach, on which I'll be speaking about half of my time now. And then for this group, really practical, for us, the Arctic is really a part as a coupled issue in the environmental forecasting. And so I'm going to be talking a little bit about the coupled prototypes that we are running right now, as particularly prototypes for our next generation subseasonal and seasonal forecast systems, which just means up to about a year out. So UFS, you probably have seen these slides before because we've been using them for a long time. So the idea is to have within NOAA, not just the weather service, but within NOAA and within the broader community, a community-developed forecast system that can be used both for research and for operations. The governance is not based on the preferences of an individual forecaster, but is evidence-based, although that is kind of interesting because there's objective and subjective evidence. We are, unlike some of the earlier community modeling efforts, not focused just on the coast-based, but we are focused on applications so that we become actionable and have a direct measure for how any improvements go into better forecasts. And this is one of the reasons why I'm a little bit less focused on the individual science issues here. The other part that is really important is that it's a unified system. The word is unified, not unitary. The idea in a unified system, and this is something that is worked out between all the line officers of NOAA about 5 years ago, as a better way of doing business. By limiting the amount of models and software packages that we have, we can focus ourselves more on the improvement of these, but we do not require a single model. We require a focus within the diversity we need to be able to do the science and the improvements. And then the whole idea is that this is really a paradigm shift, that we are really focusing on the community to work with us on getting a better forecast out. And also that the side effect of this is that we really want to simplify the way we're doing business. I could easily talk another 10 slides about the UFS, but here is sort of the high end. If you want more to know more about it, contact me and I can show you some other things. But this is really important. This is the idea of the UFS as a community approach to operational modeling, has buy-in at the level of the AAs, of the assistant administrators that lead the Weather Service, the Ocean Service, NESDIS, OAR, and the few other pieces. A real key part of this is the fact that we actually signed a few years ago an MOA with NCAR, particularly between the NCAR, the Weather Service, and OAR on infrastructure. The graphic here on the right shows you the 7 pieces of the infrastructure. The idea that we're doing community modeling, when I talk about the prototype system, you will see that the component models are all community models that come from mostly from other places than the Weather Service. The idea that research and operations is done with the same code. The fact that we actually have, since about a year, a large-scale project going within NOAA to actually resource this and to focus work on that. And then very recently, as of a month ago, we have stood up an official NOAA modeling board where the different line officers with the funding authorities now are coordinating their work to be better aligned with each other and to leverage each other's work better, mostly around the core of this unified forecast system. And a few weeks ago, the EPIC contract, which is written in law, so it's the Earth Prediction Innovation Center, which is written into the Weather Forecasting Improvement Act as a mandatory center that we're setting up to support the infrastructure and the use of, at least in stage one of EPIC, the infrastructure and the use of the UFS. And it will help us develop that further and help us do software governance for that. So this started out, I've been talking about this for years. The last time I talked to ERPIC about the UFS, this was an idea, this was not a reality yet. And so the things that make the UFS a real reality is the graduate student test that we've done, and the fact that we're actually supporting a set of applications beyond having the code available on GitHub. The example of the graduate student test is that Neil Jacobs, well before he was NOAA administrator, active NOAA administrator, working for Panasonic, needed a team of 4 or 5 people, and in several months he needed to buy a supercomputer the same as we had in order to be able to run just our global forecast system. When we went to making these codes available to the community, we did something called the graduate student test, where we wanted a graduate student to be able to pick up our system from GitHub, run it and test it in a day. And this is actually a fully coupled system. The first one we did, ocean, atmosphere, and ice. And Neil Jacobs was able, on a 10-year-old MacBook Pro, to do it in a day by himself compared to the multi-months, multi-people, and the supercomputer buy he did before. So a complete game changer in how we can work together with the community. And we have some real model releases since then. There is a medium-range weather application release, a short-range weather application release, which is basically the standalone regional version of our models. There are infrastructure components and tools that will be released, and particularly important is the fact that we're closely linked to JEDI, which has already been mentioned. And so a little bit more detail. I will run really quickly through this to make sure we stay within the 10 minutes. But we have in red a bunch of implementations in operations that are UFS based. And in blue, we have a set of model releases that have been made that are effectively supported. And I would like to put the attention on the fact that in late this year, the next version of the medium range weather application is tentatively going to be the fully coupled seasonal S2S prototype that we'll be talking on a little further in the following slide. And so what is really different here is that in the past, we would give you our operational code as a tarball from a website after we went operational without documentation. So you were lucky if you could start doing research with our operational models a year or two after we had made these things operational. Now, if you take a look at the short-range weather, the SRW application, we are not expecting this specific application to go into operations until 2023 or 2024. So our researchers can now join us with our development work much earlier. And again, this is fully supported. We're doing this because we really want to accelerate the research to operations transition. Before the UFS, with the WaveWatch model and the HFORF model, we've shown that if we use supported community models and have research done with the operational system, we can actually accelerate the process in terms of the time it takes by a factor 3 to 5. We use the same code by using the same code in research and operations, and by using the same test environment. A lot of the work does not have to be duplicated later by the Weather Service once the development work is done. And of course,
sorry to cut in, but we're coming up on time. So
okay, cool. Now let me go a little further to the prototype that we're working on. So this is you can read this at your leisure, but community FE3 model, community MOM6, community wave model, community CICE model, with a driver mediator that we share with CESM. We've been doing a bunch of prototype tests. We started out with just test running the coupled system with different initializations. That were the first 3 prototypes. After that, we started to do a little bit more stuff. What we've been doing in prototype 5 is to move to CI6 and a fractional grid. In prototype 6, we are now at a much higher vertical resolution, newer physics GFS. And why is it important for here? This is even our first out-of-the-box try. The red, the black line is the observations of the CS extent over months for 2017. The gray is what our coupled CFS used to do, and you can see these whiskers going away from the actual observation. In other words, there's a lot of drift in the CFS. The red and the blue lines, you can see there may be issues in prototype 1 with following exactly the CS extent, but the behavior is the same. There's no drift away from it. In prototype 3, when we spent a lot more time on initializing, you can see that the same behavior is still there, in the sense that we're now actually much closer still to the observations in some parts of the season, and that we don't have these whiskers as much running away anymore. So even though we're still in the setup phases of these prototypes, we're very happy to see that particularly the ice is a lot better in our coupled systems. And this is really important because when we put CFS v2 into operations almost 8 years ago, the reason why we did not do this on the smaller timescales is because the ice drift was horrendous and was not useful for our people. So, Renu, I'm done.
Thank you. Thank you very much, Henrik. There are questions, but we'll come to that after the last presentation. So the panelist for E3SM is Luc van Druckel. Luc?
Okay, stop share. Here we go. I'll take a look at the chat. So I was a little busy.
Yes.
Okay.
Yes. Thanks, Luc.
We're there. It worked. Wonderful. Now I just have to find where the slideshow button. There it is. Okay. Hopefully you can see my slides and we're good to go. So my name is Luc van Druckel. I'm on the leadership team of E3SM. And I'm tag teaming this presentation with Andrew Roberts, who's also a member of the E3SM core team. And we're, again, talking on behalf of many people, most of whom are listed here. We realized this morning we made a critical omission and forgot Elena Veneziani, who's also at LANL, who has made a lot of contributions to this work and this presentation. There we go. I think I skipped too many. So within E3SM, Arctic research is kind of cast in a global context, and E3SM has 3 primary science focus groups: water cycle, biogeochemistry, and cryosphere. I won't read these out, but we're looking at a number of things. We're thinking about energy and land use, sources of precipitation, and sea level rise in particular in the cryosphere. So all of these are very much involve the Arctic. So in our presentation, we decided we'd integrate all the questions together and focus in a couple of things. One of them is regional refinement, which is a key capability E3SM has to offer, and scale-aware physics and BGC. We'll also talk about coastal interactions and sea level rise. And then at the end, we'll touch on model observation data fusion. And again, just to stress, this is a large collaboration within DOE amongst many projects listed below. All right, of most interest, I would say that E3SM has to offer, one of the most important things is variable resolution in every single component. In particular, the ocean and sea ice models are cast on an unstructured grid, so they have seamless transitions between resolution. It's not nesting. It's not all of a sudden transitions. They go smoothly. So this is one such mesh. This is called our water cycle 14-kilometer mesh. So throughout the Arctic and along the coast, we have 14-kilometer resolution, and we transition to 60 kilometers to 30 kilometers outside of it. And you can see we get really nice resolution of shipping channels and sort of the islands through the archipelago. All right, so critical to any simulation here of sea level rise will be the effect of ice cavities and Southern Ocean interactions and ice sheet collapse. So we're working on this quite a bit. We have recently put in an ice sheet shelf capability for sea level rise studies. And again, also to stress the variable resolution, a collaboration, this image is a collaboration between E3SM, HILAT, RASM, and the Arctic Storms Project, I believe led by the University of Alaska Fairbanks. And we can drop this resolution wherever to study, and we are working on some of the scale-aware pieces that we'll talk about in a minute. So the Arctic Ocean is a part of the climate in a couple of ways. One, it interacts actively with other components, the sea ice, rivers, etc. And it's also linked with the broader global ocean. So regional resolution is important for studying this problem. And these images here are from one such mesh that HILAT RASM has been working with, the Arctic 60 to 10 kilometer mesh. And while it does, this refinement does improve some of the circulation there, such as Atlantic inflow, there are still some issues with stratification in the Bering Strait, some freshwater transports, and AMOC is still on the weak side, even with this enhanced resolution in the Arctic at 12 spherodrams. So despite those issues, this resolution does offer advantages. So we're able to capture the Arctic and Antarctic ice edge with much greater resolution. One other big challenge that I'll mention here on this slide is the ocean mixing. And this is one example of many. This is from 2 simulations we had of E3SM, our V2, our version 2 code. Let's see, I think I can use this. On the left side here is our low res mesh. So this, think like CMIP, about 0.4 of a degree is the global resolution roughly. On the top is slightly subsurface salinity bias relative to World Ocean Atlas. And on the right is the high resolution. This is global eddy resolving. And so the point I want to make here is that the transition from low resolution to high resolution really doesn't help many of the biases. In fact, you see more subsurface freshening in the high res compared to the low res. You also don't see a significant reduction in mixed layer depth biases along the bottom. This really suggests that mixed layer entrainment is quite poor, as Mitch alluded to in his presentation earlier in the meeting. So within our project, work is underway on a new closure that has improved physics, including the prognostic equation for entrainment. So I'll turn it over to Andrew for this one.
Good afternoon. So one key item we are addressing is the ability of subgrid scale parameterizations to address the scales they're representing on a variable resolution mesh. This includes resolving eddies. And for the Arctic, a classic example of this is in the column physics of our sea ice model, which is analogous to SICE, but with some recent improvements to radiation and snow. And within the sea ice model, sea ice morphology is classically represented with a thickness distribution, illustrated here, spatially left and discretized on the right. And we are working on a scale-aware approach to this so that our sea ice model will be able to understand the particular resolution of each grid cell, as well as understanding the current local occurrences of ridges, melt ponds, and built up snow using macro porosity. Of course, that's not just, scale awareness isn't just limited to parameterizations. And one really common example is this scale awareness of sea ice mechanics. So sea ice mechanics are known to be dependent on scales, and beneath about 10 kilometer resolution it has been shown that the continuum assumption for rheologies begins to break down in its ability to simulate real sea ice mechanics. Adrian Turner and his colleagues at Sandia are working on an Earth system model appropriate discrete element approach to model sea ice mechanics. And it's designed to get around the expense of current discrete element methods that have precluded them from being used for centennial scale climate simulations just due to their computational expense. Luke.
Okay, so on the
Sorry, Luke. Sorry, Luke.
This
Wrong
is
slide. It's me still. So the unstructured meshing is a real strength of E3SM, as Lucas mentioned, and has afforded us to venture to appropriate E3SM to develop coastal interactions for understanding sea level rise in a global context. So on the one hand, our ice shelf capability in the Antarctic allows us to address major source terms to future sea level rise, including in the Arctic. And on a local scale, we're able to resolve coupling processes and physical interactions such as tides that typically require quite higher local coastal resolution for accuracy. As part of this, we're also implementing land fast ice, wave ice interactions, and benthic biogeochemistry, in addition to our existing BGC capability, which is similar to that of SICE and CESM. We're also working to implement an explicit explicit Greenland ice sheet coupling. Luke.
Okay, given we're running down to the end of time, we'll kind of zip through some of these things that are new features coming online. One of them is the Greenland ice sheet model coupled in. So the MALI model, MPAS Albany land ice, has variable resolution 1 to 10 kilometers in the Greenland ice sheets. This involves some of Matt Hoffman's work on subglacial hydrology. We still have some challenges with fjords that some within the group have worked on a little bit. Teresa Morrison, who was here while doing a PhD at Scripps. And there's also initialization issues that are being looked at under the SIDAC Prospect project.
And on the wave side, we have WaveWatch 3 working on an unstructured mesh in the Arctic to get around the problem of grid convergence. And we also have explicit tides working in EMPAS Ocean, and we're currently coupling that in E3SM to enable ice tide interactions, both in the Arctic and the Antarctic. Luke.
For Arctic BGC, we have 3D BGC and sea ice. We have all the coupling in place. We're about to introduce supercycling and tracers to improve the performance by a factor of about 2. And a benthic model is on the way as well. We also have a number of challenges that are common to a lot of BGC, and these are often physics, BGC coupling, mixing is one, data issues, lack of resolution, etc.
And finally, E3SM as a project has a real interest in exploiting machine learning and artificial intelligence. And in the lead up to more sophisticated methods, we're working on observational emulators to be able to convert model quantities to observational equivalent quantities, which are a lot easier to work on. The example I'm giving here is an IceSat emulator where we sample the model at the same time and place for its freeboard, not its thickness, as for IceSat overpasses, which allows a rigorous evaluation of sea ice mass and its performance using freeboard as a proxy.
Okay, and finally, we'll just leave up collaborations here. We'll just have less than a minute to go. Many of these have been mentioned before. There's a lot of opportunity even within DOE, but within the broader community as well. One thing we think about within E3SM itself is how to work better with the what we call ecosystem projects, and have recently launched a project that I'm in charge of that is working with these things. Some other things that others have mentioned: ensembles, uncertainty quantification, data assimilation, etc. We also are heavily involved with SICE Consortium, and then looking at these new data fusion efforts as well. And we'll end it there.
Thank you very much, all of you. This has been a very good series of presentations. Unfortunately, there's been a lot of information and we're running out of time. We can stay on for an additional 10 minutes, I'm told. With that, I think Jack Dibb has been waiting with his question for a while. So Jack, you get the chance to ask the first question.
Well, I'll ask the question and listen to some of the answer because I have to go to another meeting at 4. But one thing that's occurred to me is that almost all of these models need to consider an observation. I was at a PACES workshop yesterday, and there was 2 big summaries of how huge numbers of models CTMs were doing with transport and speciation of aerosols in the Arctic. And they're all still doing pretty badly. And to me, it seems like this would be important for surface energy balance and cloud interactions and snow albedo and ice albedo. And none of these groups mentioned this as a challenge. So somehow they're all treating radiation, but not getting the aerosol part right. And I just, anybody comment on what your impression of that problem is? But I do have to go in about a minute.
Well, if I could just answer here quickly, I think that a lot of the groups have indicated that clouds are a particular difficulty. And so we've been trying to go to 2-moment cloud microphysics. Of course, NCAR uses 2-moment cloud microphysics. The issue, of course, is that there's not a whole lot known about the aerosols associated with that. So it's not just simply the the aerosols by themselves, but it's the aerosol interaction with the clouds as well. And so I do think that that's kind of a significant issue. I think we would like to go through more observational data to understand how our models are working. And so there is Mosaic, and I believe there is some data that might be useful from that, but also there's this upcoming NASA aircraft field study called ARC-6, which might also be of use for understanding clouds and aerosols as well. So I think our major challenge is to get more observations.
Any other group wants to tackle it?
Sure.
Or provide
Sure.
your perspective? Yeah, go ahead.
Yeah, so we spent a lot of time a few years back on building on new architecture and new die cores with the understanding that the real improvement of the models were going to be in physics. And so if you look, this is not just an Arctic problem. This is a place where we are now really focusing in the next few setups on looking at what we need to do to get physics better in general. And if you look at it from weather forecasting and all other kind of places, the idea of bringing air quality and tracers directly into the model, both for the model physics and, by the way, for more accurate retrievals of satellite data, as well as, for instance, the fact that we're actively working on bringing smoke into our models, as that has a big impact back on the physics too. So I 100% agree with you, except for the fact that this is a problem all over the place. This is not just the Arctic. And at least at the Weather Service side, there is definitely, by design, a switch over to look from a scientific perspective much more to the physics of the atmosphere.
Okay, well, thank you both for those answers. And I would just say that I agree that it's a problem everywhere, but the Arctic seems to be severe. And anyway, thanks all, and I got to go.
If I could comment a little bit on the aerosol component. Yeah, I agree with Richard and the previous speaker regarding the aerosol components over Arctic. And we currently have an ongoing project looking at aerosol impact on sea ice. It's an interdisciplinary science project. So currently we evaluating all the reanalysis products, although it's very challenging for all the aerosol reanalysis product to assimilate observations, because there is almost no remote sensing product like from MODIS, MISR, or Calypso. So it's very challenging because of the high surface reflectance and very high signal to noise, noise to signal ratio. And so the initial thought is that reanalysis wouldn't have much skill over Arctic. However, we found that actually, because maybe most of the aerosols, especially
So, Peng Xiang, have you cut off?
Sorry, hello?
Yeah,
we have. Oh, sure. Sorry. Oh, so I would say we find some skill from the reanalysis. We have less divergence compared to the AOD field compared to climate models like the AirCom climate models, and we also find that there are very large interannual variabilities in AOD, like within like the past 20 20 years. And then that mainly caused by biomass burning smoke in the spring and summertime. So we kind of come up with provide some background information for field campaigns because and case studies because field campaigns can only tackle a certain time period and locations, and those can be potentially impacted by those very large interannual variabilities in biomass burning smoke. So it's good to see those climate models start to include biomass burning smoke in their model. So thank you.
Thanks. And you will you were from which group? I missed that.
Sarah, I'm from the Naval Research Laboratory in Monterey, California. So we have, thank you. We do aerosol reanalysis to look at the 3 currently available reanalysis for aerosols, including Mara2, NAPS, which is developed here at the Navy, and CAMS, CAMS-RA from ECMWF. So, thanks.
Thanks. Does anyone else want to respond to this question, or I know we're running out of time. Marika, I see you unmuted.
Well, I'll just say, I mean, we have ongoing work to try and better simulate and improve aerosol and aerosol cloud interactions within CESM. So this is it wasn't highlighted in my slides, but that doesn't mean that there's no focus on it within the context of the project.
Okay. Great. So I do have a general question, and I was wondering whether I could quickly hear from the panel members as to what do you think are the low-hanging, based on the fact that you've heard other people speak, what do you think is something that we could potentially work on or benefit by collaborating a little bit more? I see a lot of activities and there are one-on-one collaborations, but is there something that you can think of across the modeling centers that could help?
You want me to answer that, Bruno?
Sure.
So from my perspective, from sort of a systems perspective, I think we've made a giant step forward by taking CICE as a model out of DOE and making it a community model. And I'm really excited to see that although there was a lot of pushback originally when I suggested that this model is becoming really an infrastructure with options rather than a single model. And by doing that, we get a research tool that is useful both by research and operations. And this is one of the reasons why, even though it's really a coalition of the willing, NOAA actually provided explicit funding for code management building this way. So that's one. On the science side, I do think what the earlier question was, being a weather service guy and looking a little bit more to the atmospheric side, just not just a question of aerosols, but using better atmospheric physics that do a better job with severe weather and with convection scale weather even. And then if you look at the number 1 issue we have with the atmospheric physics, or one of the big issues that we have in Alaska, is this stratification in valleys and complete decoupling of the flow in many cases that we do very poorly in any of our models. So that's not an over ice problem, but it is an Arctic problem. It is a high latitude problem. So these are sort of the 3 major things I'm looking at: the better architecture and going that way with CICE in a coupled environment, the atmospheric physics on top of anything that happens in ice, and then I already forgot my third one.
So
the decoupling and stratification. Yeah.
Thanks. Anyone else wants to take a shot at that? Yeah, Mitch.
Yeah,
go
I'll
ahead.
make I would personally love to see more intercomparison of the Arctic Ocean simulations. We focused a lot on sea ice over the last 20 years, which is great. Still have a lot of issues there, but to me, the Arctic Ocean just seems very understudied, and a lot of centers don't even really know what their model biases are in the Arctic. Of course, that's somewhat hampered by observations, but I would argue we have enough to provide some pretty powerful constraints on our models. And I think I would love to see some intercomparisons amongst this group regarding the Arctic Ocean, and then also bring it towards the model physics side and start asking the question of how can we improve the model physics to represent the Arctic Ocean properly. My impression is that kind of the Arctic has sort of come along for the ride in a lot of ocean models, and these mixing schemes are developed, elsewhere in the ocean, in the mid latitudes and tropics, and then they just get placed in the Arctic. But the Arctic is such a different mixing environment that it really needs a special treatment, I think, in terms of physics. And I would love this group to really dig into that problem, kind of collectively, leveraging the different vertical mixing schemes that are being used in the different models.
I think that's a great idea. I'll just chime in.
I'll chime in too. That's spot on.
That's wonderful. I actually thought, among my list of things, I thought maybe suggest a MIP, but I didn't want to overwhelm people with MIPs, but maybe process-oriented MIPs that can help is something that we can potentially follow on from here. Any other questions?
Only to say that Luke's working on a new mixing scheme for the Arctic, but he doesn't have any power at his home right now. So I'm sure he agrees with Mitch.
So one quick comment to all the modeling groups. Nobody mentioned the existing issues with coupling ice and ocean, which is related to the mixing and momentum transfer. I wonder any comments from the presenters. I'm talking about levitating sea ice in the coupled system.
We don't levitate.
Do any of the panel members want to take that?
I'm not sure if you just heard me, but for the E3SM side, we don't do that anymore. So our models, our sea ice is floating. Yeah, nor do we levitate. I think James has some interesting thoughts on landfast sea ice, which is clearly not levitating, and he may also have some thoughts on the ice ocean drag. How to refine that.
I'm here. I'm not sure exactly what the question was. Levitating sea ice. I think we do have levitating sea ice still in the GISS model.
No, HiCom does, but not the GISS.
Oh, okay, in the HiCom version. I do have a question for Mitch though. In terms of the sea ice thickness distribution that Mitch showed from the GFDL model, do you have any idea why that the thickness distribution has shifted so far towards the Chukchi Sea rather than towards the Canadian archipelago? Do you think that's a wind-driven?
Yeah, so it's not wind-driven. If you run a reanalysis forced ice ocean run, you get a similar looking bias. It's a little bit muted compared to the coupled model, but it's a very similar shape actually. So even putting in the right winds, you still get the same bias, which I think is kind of exciting because to me it says it's probably a CIS model physics bias. And it seems to me that the ice is flowing into the area north of Greenland, and it's simply advecting too easily into the Beaufort Sea in our simulations. So we think maybe the ice is just a little bit too weak with respect to shear stress. But that's sort of our initial hypothesis, and we want to play with maybe just changing the eccentricity of the yield curve, for example, and see if we can maybe stiffen the ice up a bit with respect to shear. But it's still a pretty open question. So any thoughts you have, I'd love to hear, maybe offline or right now.
Yeah, well, just briefly, we see the same thing in the GIS model. Also, forcing with reanalysis data, we can't constrain the Beaufort Gyre to be kind of close enough to the Canadian archipelago, to the Beaufort Sea. It stretches out into the Siberian Shelf, which could account for the thickness bias.
Interesting. Well, we should definitely talk more. It'd be great to keep this going.
Yeah, sounds good.
Great.
So thank you very much, all the speakers. This was really good. And the point is that it would be nice to keep the conversation going, and we'll think of a way to facilitate that. But next time we promise to stick on time. So I'd like to thank all the speakers and all the collaboration teams that have joined us. Thank you very much, and looking forward to more work into the future. So thank you.